Alright, welcome back everyone. In this video, we're going to take a numerical approach. Earlier we took an analytical approach to solving the equations that model the blending tank problem. And in order to execute our numerical approach, we shall be using Simulink, as you guys have already guessed it. So once again, here I have the schematic. I have the inlet flow rate at 2 kilograms per second, and there is a certain mass fraction, the inlet mass fraction being 0.05. And let me just edit this. I want to emphasize that this times all the inputs could vary. So my stream 1, the flow rate of stream 1, the mass fraction of stream 1, along with stream 2, as you can see, there are a total of 4 inputs this time. So there can be 4 disturbances to our system, and of course our output variables are going to be the outlet flow rate, of course, and also the outlet concentration. Both of these need to be modeled so that we can implement a control strategy. So next up, and obviously, I forgot something very critical. Not to forget our impeller, so that we have the well-mixed assumption. Okay, the well-mixed assumption is still gonna be valid. So I have my initial steady state values for my outlet mass flow rate and my outlet mass fraction, and you guys can get do this as an exercise, and hopefully you'll get the same values. Well, not hopefully, you will get the same values if you do the steady state algebraic equations, if you solve them correctly. All right, just to give you a peek back at the schematic. Now moving on, the model. Here I have the first equation is the total balance. Let me just emphasize that. Total balance, total mass balance. And the second equation is the component balance, the A balance, as you can probably see. And these equations have already been derived. These equations have already been derived in the previous video. Okay, so if you have trouble deriving one or both of these equations, just go back to the earlier videos where I've been going through this tank problem. So now, once we have the initial conditions, and now we have one algebraic equation and one first order differential equation. Now we need to get a Simulink sketch. I'm gonna try to draw how my block configuration is gonna look like. Sketching my block configuration before jumping into the workspace of Simulink can save me some hassle, especially when you have multiple equations that you need to model. Drawing a sketch is like writing a pseudocode. It really makes your process faster in the long run. So let's start. I have, excuse me, give me 1 second. Okay, I have a total of 4 possible inputs. Let's zoom out a little, because this is gonna get, hopefully this doesn't get too messy. I have 4 inputs, I have 4 inputs, and my inputs shall be represented as step blocks. So first one, I have M1, the flow rate of stream 1, XA1, the mass fraction of stream 1, M.2, mass flow rate of stream 2, and MXA2, the mass fraction of stream 2. All right, so the first equation is just a total mass balance. So I just need to take M1 and M2 and apply the addition operation. Just a simple addition operation is going to give me M3 of t. Let me just highlight that. I'm going to highlight that in yellow, M3 of t. Okay, our next equation is going to be slightly more complicated. So we have the product terms. As you can see, we have products of mass fractions and mass flow rates. products of mass fraction and mass flow rates. Okay, so let's see what we can do. So first off, M1 XA1, we need a product of these two. There we go. Oops. All right, let's try that again, shall we? All right, there we go. And yep, that's the product. And that right here is gonna be, I'm gonna label it as XA1 times M1. All right, so all right, I keep forgetting, I believe the horizontal were dominant when you were drawing your flow sheets. I believe the horizontal is the one that's dominant, but it doesn't really matter. We're just sketching right now. We're just sketching. Okay, so this right here, X1 times M1. Now similarly we can get, as you can see, oops, let me try that again. I'm gonna do the same thing for stream 2 and XA2, multiplication, products. And all right, so now we have XA1, XA2 and M2, my bad, XA2 and M dot 2, my bad. And now both of these are inputs. Both of these are inputs. So both of these go through an addition operation. Actually, let's extend that. Both of these go through an addition operation. And there's also the output term, XA3 multiplied by M dot 3. That's going to be subtracted. There's going to be a subtraction here. And obviously XA3 is one of the outputs, so we don't have it yet. But that's not going to stop us, will it? I'm just gonna assume that this is where XA3 is coming from. And we're gonna loop it back, as some of you can already see what's gonna happen. So yep, and this right here, once you divide it by 1 over the mass of tank, and I forgot what was the mass of tank. Just give me 1 second. That's not going to be that much of a problem. All right, now this term right here, let me finish the sketch. This term right here represents dxa3 dt, and once you integrate it, you're going to get xa, the outlet concentration. Let me just emphasize that in the correct color scheme, xa3. And boom, we're now, as you guys can see, we can loop it back. We can loop this back. There we go. How nice. And obviously we want to visualize this. We want to visualize the output concentration. So we're going to send the output to a scope. That's my sketch of the scope. Okay, so in this video, I'm going to finish this video by just I'm going to conclude this video right here by just showing you the sketch. In the next part of this video, we're actually going to jump into the Simulink workspace and just sketch this out. And you guys can already see now our working in Simulink is not going to be a problem at all, because we've basically sketched our block configuration and there seems no issue so far. And yeah, I'll see you guys in the next part of this video. All right, thank you.